All right, let's talk about Activity 416 moments. This is a refresher from back in levers. We talked about moments briefly. So just to refresh our memories, let me go ahead and bring up the moment equation on my iPad and work out an example for you, just so we can understand the idea behind moments. So moment is equal to force times distance, where force and distance are perpendicular to one another. A moment is essentially the turning effect of a force. And so let's say I had some built-in and cantilever, and I have some force at the end. Let's say it's, oh, I don't know, 400 newtons. Okay. And we know the length of this cantilever is 6 meters. The line of action of the force and the member that the force is acting upon are perpendicular to one another. So this force here is going to cause a turning effect where this cantilever is going to want to turn. It's going to want to rotate, counterclock or actually clockwise. So this turning effect of a force is going to want to cause clockwise rotation. And we can calculate that force or that moment by taking the magnitude of that force, which is 400 newtons, and multiplying by my perpendicular distance, which is 6 meters. So that is going to be equal to 2,400 Newton meters. Okay, so that's the moment that force generates. Okay, pretty straightforward, right? So some key things here is that the moment or the force has to be perpendicular to the line of action, or the line of action of that force has to be perpendicular to this point of rotation. So the axis that passes through that point of rotation. So my member is horizontal. I should be looking for a vertical force that makes it perpendicular. And so force times distance will give me my moment. If I had some force that was acting at some angle, so let's suppose that my force was, acting at an angle like this of, 600 newtons, and we knew that this was, a 45-degree angle. Then that moment that's generated by that force, again, has to be perpendicular to the distance from the line from that point of rotation. So here's the line of action of my force, but my point of rotation, this point back here, this is 45 degrees. It's not perpendicular. So only the y component of this force causes will cause the turning effect, not the full 600 newtons. So I can replace the 600 newtons with a force in the x direction and a force in the y direction, such that the overall effect on the body is the same. So the only the y component of this force is perpendicular to the member itself that'll cause rotation about this point of rotation here. So what we have to do in a situation like this is find what that perpendicular force is, or in this case, the y component. So as you recall from my force vectors lesson, we have a 600 Newton force that's down into the left, down into the right. So it's going to have a component that's downward, and that downward force there is what's going to cause that have that tendency to, for this to rotate. So this is 45 degrees. And so this is my y component of that force, and this is the x component. We know the x component is parallel to this distance here. And so the x component does not cause rotation. So I'm only interested in the y component. So this is opposite of the 45-degree angle. So I can use my sine of 45 degrees is equal to opposite, which is my y component, over my hypotenuse, which is 600 newtons, and multiply by 600 newtons on both sides. Excuse me, I didn't mean for this to come up. That drops out, and I'm left with, and I can go to bring up my calculator. So let's see, 45 sine is 0.707 multiplied by 600, and that gives me 424.26. So the y component of this force vector is 424.26 0.26 newtons. Okay. So now we're no longer looking at, if I go back to this equation, we're no longer looking at this 600 newtons alone because 600 newtons is acting at an angle. It's not perpendicular. This line of action of this force is not perpendicular to this distance. But what is perpendicular is the vertical component of that force vector. So this y component, this 428 or 424, excuse me, 0.26 newtons is what's going to cause or have the tendency to want this to rotate. Okay, it's the turning effect of this force. So times 6 meters, and so I can multiply that by 6, and that is a moment of 2,545.6 Newton meters. Okay, so that's the moment that's generated from the 600 Newton force that is acting 45 degrees counter or clockwise from the positive x-axis. So this force is down and to the right. All right, so that's the idea behind moment. So in this activity, what we're doing is we are going to look at moment in an engineering context and conduct moment calculations. The resources here, you're going to need some VEX components because you're essentially going to make a lever assembly with VEX. And you can use these hook weights or these mass sets to essentially investigate the idea behind moment. Now, what we're doing in this activity is it's all a balancing act. So when you open up the spreadsheet, it'll look like this. It's pretty helpful if I think I have a spreadsheet in my shared drive that has an image of the lever. But what we're doing in this spreadsheet is you're going to be placing these different masses a certain distance from the fulcrum. So, for example, this 100-gram mass is going to be placed 8 holes from the fulcrum or the axle. Okay. So this is on the left side. So it's kind of hard to see, but this is the left side of my fulcrum. And this over here is the right side of the fulcrum. Okay. And so the idea here is that we're going to only put one mass on the left side. And then we're going to put, starting with one mass on the right side, figure out how far those have to be from the fulcrum to balance out this lever. And then at some point, you're going to add 2 masses and figure out, well, where do I have to put these 2 masses so that it balances out the lever? And so in order to attain static equilibrium is when my left side moments, so actually, let's go ahead and look at it from here. So static equilibrium is going to be attained when the sum of my moments is equal to 0. In other words, the moments on the left side of my fulcrum have to equal the moments on the right side of my fulcrum. So if we hang a mass at this point, and we know that this distance, or we know this distance rather, we can go ahead and determine what the moment is. Now, this is a mass. Remember, to calculate a force, we take mass and multiply by acceleration due to gravity. So if I have a 200-gram mass or a 100-gram mass, this is just a on shape mass. So I don't know exactly what mass this is, but let's suppose it's 200 grams, right? So let's suppose we're hanging 200 grams here. So that 200 grams is really equal to a force of, let's go ahead and convert this to kilograms. So 0.2 kilograms times acceleration due to gravity, which is 9.81 meters per second squared. And when I multiply these two together, I end up getting my my force in newtons. Okay, so this is roughly 10. This is 0.2, so this should be about 2 newtons here. So let me go ahead and bring up the calculator so we can actually calculate this out. So 9.81 times 0.2 gives me 1.962. Okay, so 1.962, or let's just go with 1.96 newtons. Okay. Now, what we know about Vex is that each one of these holes is half an inch apart. So right now this is 1. So my fulcrum is right here. So 1, 2, 3, 4, 5, 6, 7, 8. So 8 holes would be a total of 4 inches. Because again, each hole is half an inch apart. So the moment that's generated on the left side is 1.96 newtons times 4 inches. Oh, let's fix this. I am mixing up units here. Okay. So I'm going to want to convert. I don't want to mix metric and imperial. So I either work everything out in imperial or everything in metric. And since I've already got this in newtons, let's go ahead and just convert that um, to meters. So 4 inches to meters. I'm going to just do the conversion on my phone. You can look up the conversion factor. So that's 0.102 meters. Okay. So point, erase that, sorry. Wait a second. So 0.102 meters is that distance there. Okay. So whatever moments I have on the right-hand side, I have to balance that out. And so that calculates to 1.96 times 0.102. So that's equal to 0. Let's say 0.2 Newton meters, just about. Okay. So the idea behind this activity is that if I had different masses, or if I had, let's say, 200 gram mass, so another 200 gram mass, where would I need to put this to balance it out? Well, if this is 1.96 newtons, in order to get it to equal the moments on the left, I also have to put this 8 holes away from the fulcrum so that my distance is the same. But what happens if my mass was twice as much? So let's suppose I hooked both of these together. Well, that means my mass is twice as much, my force is twice as much. So in order for this to balance out, I need to have this half the distance. And so only 1, 2, 3, 4 holes away. Because what will happen is my force will double. In order to get this moment to balance out with the moment on the right, then I have to decrease my distance by half, since my force increased by two times. So the idea behind this activity is, at least the first part of the activity, let me clear my drawings, is that you would, in your class, have the students build a lever, simple first class lever. You have these hook weights or these mass sets in your classroom, hopefully, or you can use something else and just know what those masses are. And you investigate. So as I have a 100 gram mass on the left-hand side, where do I need to put a 100 gram mass on the right-hand side so that this is balanced? So we know that for moment in the metric system, the units are Newton meters, right? Force in newtons times distance in meters, or in the imperial system, it'd be pounds, inches, or pounds, feet. Just for the sake of working out the math here without doing any sort of conversions, you can just say, you know what, we're going to use the moment that a unit for moment nobody ever uses, gram holes. So 100 times 8 would be 800 gram holes. And in order to balance out on the right side, this also has to equal 800 gram holes. So where do I need to put this mass? Eight holes away from the fulcrum on the right-hand side. This right here is 1,200 gram holes if I multiply these two. So where do I need to put this one so that it balances out with the 1,200 on the left side? Or if I have a 200 gram mass, where do I need to put that? Well, to get 1,200 gram holes, we put that 6 holes away from the fulcrum. This right here is going to be 4,000 gram holes. So where do I need to put these two 200 gram masses on the right hand side so that it equals this 4,000? Well, let's see. If I combine them and hook them up together, then that's 400. So I can put both of these combined at 10 holes away from the fulcrum. So I have 4,000 gram holes on the left side. I have 2,000 gram holes on the right side, plus another 2,000 gram holes on the right side. And so I'd have to combine both of those on the right side at the same hole. So 10 holes away from the fulcrum. So if this is, what is that? Eight holes. So let's suppose that this is a 500 gram mass, 8 holes away. Okay. Then I would have to put these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I would have to put these two 200 gram masses. So again, we're saying that this is a 500 gram mass. And these are two 200 gram masses. So 400 grams. To get that to balance out, we'd have to put those 10 holes away from my fulcrum. And that's going to give me 400 times 10. So 4,000 gram holes. This is 500 times 8 holes. So yeah, 4,000 gram holes as well. But again, that's just an imaginary unit. That's just to help with the idea behind balancing this out. What we need to do, and they do it on the next tab, but steps 19 and 20 are no longer part of the activity, so I'm not sure why this is still here. But the idea behind this is that instead of using grams and holes, you convert your masses to newtons, and you convert your hole distance to inches and then to meters. Okay. And so here's those distances in meters. And then you fill out the table. And the idea here is that, and they really combine this. I don't like the way this is combined because the sum of the moments is not just the right side, it's the sum of the left and the right side. So let me go ahead and only do this here. This is the right side. So these are all the moment calculations for the right side. This right here is all the calculations of the left side. The idea here is that the sum of the moments should be 0 if you have balance. Now, how are they going to sum up to 0? Well, when we talk moments by convention, so just like in when we're talking forces, and in physics, if we sum up, forces in the x direction, by conventions, sometimes we say, well, any force going to the right is positive. Or if we sum up forces in the y direction, we say any forces going up are positive. Well, when we start summing up moments, by convention, we say anything counterclockwise is positive. Okay? So counterclockwise moments by convention are positive. So all my left side masses here are going to want to cause, if I take a look at my assembly here, when I place a mass on the left-hand side, it's going to want to rotate like this. So that's a counterclockwise rotation. So all the moments on the left-hand side here, all of these moments will be positive, right? So positive moments. All the moments on the right-hand side will be negative moments because they will generate on the right-hand side clockwise rotation. And on the left-hand side, you're going to generate counterclockwise rotation, or by convention, positive. So that way, when you sum them up, it equals 0. So going back to that example over here, This is generating, and again, I'm going to use the fake belief units here of 8,000 or 4,000 gram holes, this 500 gram mass, 8 units away. So this will be, positive 8,000. Again, this fake believe unit of gram holes. And then over here will be negative 8,000. Oh, no, not 8,000, 4,000, excuse me. Because it's 500 grams and we're 8 holes away. So that's 4,000 gram holes. And here we have 400 grams. And we're going to put this 10 holes away from my fulcrum. And so that's negative 4,000 gram holes. So when you add these up together, you have positive 4,000 plus negative 4,000. And so that sums up to 0. So what you should see on this second tab here, if you were to take it this far, is that all of these should sum up to 0, showing that you got a balanced situation. Okay. However, again, steps 19 and 20 are no longer part of the activity. Really, just these first steps are. Okay. Just balancing out the masses and the distance from the fulcrum. So if we take a look at this first part of the activity, it talks about that balancing act. Okay. So hang a 100 gram mass on the 8 hole, predict where you need to hang a 100 gram mass on the right side so that the beam is balanced. So if I have 100 grams, 8 holes on the left, then I need to have 100 grams, 8 holes on the right for balance. So test your prediction, hang the 800 gram mass or the 100 gram mass, see what happens. Okay. So then you go and record that on this table here. Okay. Just on the first tab. Then it says removing both masses, go ahead and hang a 100 gram mass on the 12th hole. So you come back over here. And now instead of the 8th hole, you have to hang it 1, 2, 3, 4 on the very end here. So you have to ensure that you build a lever that gives you enough distance so that you can hang it 12 holes away from the fulcrum. So you'll have to use the longest 1x piece to make that happen. And then put the fulcrum or the axle right at the center of that. So you end up with that 12 holes on the left side and 12 holes on the right side. So if we're going to hang a 100 gram mass on the 12th hole on the left, where do I need to hang a 100 gram or 200 gram mass on the right? Well, here I have 1,200 gram holes. So 200 gram mass on the right hand side would have to be 6 holes away. 6 times 200, 1,200. Okay, so again, we're using that fake believe unit of gram holes for moment. And that's why in this activity, they take you, and previously they would take you to the next step and actually have you convert into actual units for moment by converting the masses from grams to newtons and the hole distance from holes to meters. Okay, knowing that each hole is half an inch apart, we can then convert from inches to meters. So we can get Newton meters for my moments. So moments on the left should balance with moments on the right so that the sum of them is equal to 0 because my left side moments are generating positive moments because they're counterclockwise. My moments on the right are generating clockwise moment. So they're negative. So when you sum them up, they should be equal to 0. So that's the first part. So then we go to 500 grams. All right. And then you have 200 grams. We just looked at that. And then we continue on. Okay. So you're pretty much just filling in this first part of the table. Okay. Or this first tab, this table here. Okay. So that's the first part. The next part of the activity talks about mathematical moments. And so you have this, beam, what happens as I slide further out one way or the other. The moment, increases either positive or increases negative, depending on what side. So on the left-hand side, you have a positive moment. On the right-hand side, you have a negative moment because of the direction of rotation. So it talks about moment being a vector quantity because it has direction, and it also has magnitude. And so by convention, anything that causes a counterclockwise moment will be considered positive. Okay. So here they give you an example, 100 newtons, 0.2 meters away. So this line of action of this force is perpendicular to this distance to the point of rotation. So that's 100 newtons times 0.2 meters. And you can calculate that out. And the rotation of this, if I were to apply this force, it's going to want to cause counterclockwise rotation. So this would be a positive moment. So when you calculate this out, your answer should be positive. So moment is equal to positive 100 newtons times 0.2 meters. Okay, so what is that? 20 Newton meters. Okay, so that's the moment generated by that force. All right, so then we get into um, the next question. Uh, we have 100 newtons, 0.3 meters away from this point of rotation. The line of action of this force is perpendicular to this 0.3 meter distance. So I just have to multiply these two, force times perpendicular distance. This is going to generate a clockwise rotation. So this will be a negative moment. So 100 newtons times 0.3. So this will be 30 Newton meters, but that's going to be negative. Okay. And this is newtons here, not, let me fix up this N here. So, all right, so 30 Newton meters negative because it causes a clockwise rotation, so a negative moment. All right, and then we get into this check for understanding, talks about that. And then we have these examples that I kind of went over earlier. So here we have a 100 Newton force that's at some angle. Okay, now we're told that this angle is 60 degrees. So the line of action of this force is not perpendicular to this distance that we're given. But what is perpendicular is the y component of this force. So if I took this 100 newtons and I created a right triangle from the components of the force, here's my right angle, the y component would be perpendicular to this 0.2 meters. So what you have to do is you'll have to use sine. So sine of 60 is equal to opposite, which is my y component, divided by hypotenuse, which is 100 newtons. And so multiplying by 100 newtons on both sides, you end up with the y component equal to 100 newtons times sine of 60. So go into our calculator, 60 times, or 60, sine of 60 is 0.866 multiplied by 100. So that's equal to 86.6. So my y component that causes that turning effect is 86.6 newtons. And so that's the y component that actually causes the rotation. So my distance is 0.2 meters. The y component of the force that causes that turning effect is 86.6 newtons. And so the moment generated by this 100 Newton force that's at an angle is going to be equal to 86.6 newtons times 0.2 meters. Okay, so you have to break up that force into components. The x component, right? If I were to replace this force with an x and y component, the x component is to the left. I haven't calculated that out, so I'll just put f sub x. This force here is parallel to this distance, the point of rotation. All right, this force is acting on the line that passes through the fulcrum, or this point of rotation rather. So this x component has no distance from this point of rotation, so the distance is 0, so it doesn't generate moment, because if my distance is 0, then, oops, I wrote the equation wrong. Moment is equal to force times distance. So I have an x component, I have a force, but there's no distance from the line of action or that passes through this point of rotation. So the distance is 0. So this x component doesn't cause rotation about this point. The only component that does is my y component. All right. So you can see some additional examples there. And then they talk about feeling the moment. Okay. So you could they suggest that they want the students to qualitatively feel the moment. And so one of the things that we used to do, and one of the things you can do, is this was back during COVID years, and so I had this PVC pipe and I just drilled some holes. And what I did was I took this mass and I kept drawing it out further and further from this supporting point, and you can actually see the PVC starts to bend as my moment increases. And as I put this mass further and further out, guess what? It got harder and harder for me to hold. So that's the idea behind this feel the moment. Part of the activity is they want students to feel the moment. And then they can also calculate it as well. So if we know what the mass is, I can convert that to a force. And so here I have a 500-gram mass. So that's 4.9 newtons. So if I know my force and I know the distance I'm placing this away from this supporting point here, or this point of rotation, I can go ahead and calculate the moment generated by this mass. The further and further I put it away, the greater my moment's going to be. So in this part of the activity, in 17, 18, 19, and 20, they want you to essentially test that out and have the students feel it. Now, when you get to a point where you have this example of Wanda, the window washer, and they ask you to determine the forces on the tension forces here at B and the tension force at A. And they assume that the platform is weightless. Now, if Wanda was at the center, each of these would be 400 newtons, but she is off center. Now, students say, oh, well, it should also be 400 newtons. No, and you could have them feel that it's not. So, talking about that qualitative feel and sense of moment, one of the things I did is I had, a student stand on this side and I had a student stand on this side and they held a meter stick. And the meter stick I had, different holes drilled into the meter stick and I used a paper clip with a string and I hung like a 5 pound plate, that you would use in a barbell or, a bench press, 5 pound plate. Right, and you put it to the center and you have them feel it, and then you put it off center. And when you get this closer to this person, it becomes a little bit. Let's see. The moment that's generated. I'm gonna have to go test this out, but they feel a difference in how much they hold, and how do they feel that difference? Well, I put it closer to one person than the other person. And what happens is you have them feel how much force it takes to hold that up, and then you have them switch positions. So you have them switch places, and so you stand in the center, you hold the meter stick, and you allow them to switch places, and then you ask them again, does it feel the same? And then one of the students that feels more force goes, oh no, I can feel a difference in it. Thus proving that when Wanda is off center, these two forces are not the same. So how do we figure that out? Okay. Well, let me go ahead and draw this. We have a force FA here. We have this force FB here. And I have Wanda's weight or force of 800 newtons here. And we know the distance here to here is 5 meters. We know the distance from here to here is 1 meter. Okay. So we can figure out what these forces are. So what you have to do is you have to choose a point of rotation when we're going to work out a moment problem here. So I'm going to suggest that A be my point of rotation. So I'm going to take the sum of the moments about point A, this point right here. Okay. So I'm going to ask myself what forces will cause this to rotate about point A. Okay. Well, if I apply an 800 Newton force here, this is going to want to rotate clockwise. And so this 800 newtons will cause a moment about point A. So that is equal to 800 newtons times the perpendicular distance of 5 meters to that point of rotation. Now, this moment is causing clockwise rotation. So if I hold it here and push down here, this will rotate clockwise. So this will be a negative moment. Okay. What other forces will cause rotation about point A? Well, this force B at the end here will want to cause rotation. So let me go ahead and add that moment. That moment is equal to this unknown force B times the distance, perpendicular distance, which is 6 meters from that point of rotation A. Okay. Now this also causes a clockwise moment, so this is also negative. What about this force A? This force A goes right through that point of rotation I'm setting here. I'm evaluating the moments about point A. So that force A has no distance to that point. There's no horizontal distance from that point of rotation, so this force doesn't generate a moment. We know if this is in static equilibrium that the sum of these forces has to equal 0. So now I have an algebraic problem that I can solve for this unknown force in B. So this 800 times 5, that's going to be negative 4,000 Newton meters minus, let's go ahead and do this, 6 meters times FB, force in member B, that equals 0. So now I can start moving things around and isolating my variables. So by isolating this algebraically, I move the 4,000 Newton meters to the right-hand side. So I add 4,000 Newton meters to both sides. And then I divide by negative 6 meters. My meters cancel out. So the force in member B is equal to, let's see, what'll that be? That's going to be equal to, let's see, 4,000 divided by 6. So 667 newtons. Negative. Okay. So what that means really is that my direction was wrong. I drew my force downward, but we know that if this is, if Wanda steps on this, the tension is actually, these cables are going to pull up. And so this force is actually upward and not downward. Okay. I assumed that it was downward. My answer is negative. And so what that means is that this is actually upward. So if I were to go back and redo this with that assumption of that it should be pulling up, same thing with A should also be pulling up, then that changes my equation. So this is still downward, so it still causes a clockwise rotation, so that's negative 4,000. But if this is upward, it causes a counterclockwise rotation, so this is positive. So now what happens is when I move the 4,000 to the other side, this becomes positive, end up with positive 667 newtons. And so had I assumed the correct direction initially, my answer would have been positive, showing that it is 667 newtons. So the closer Wanda is to this force, this person over here is gonna feel more force. So it's not split in half if this is not in the middle. So when Wanda is off center and more to the right, the tension in this member B here is greater than if she was on the left. or than if she was in the middle rather. Okay. Now that I know what that force is, I can go ahead and figure out what the force in member or this force in FA is because I can just look at the forces in the y direction. I essentially have a free body diagram here. Now let's go back again. I goofed and assumed down, but I know that these two should actually be pulling upward, right? To hold up this platform with Wanda, these two should be pulling up. So when I look at the forces in the y direction, I look at my free body diagram and I say, okay, well, I have FA that's going upward. I have FB that's going upward. And then I have this 800 newtons that's going downward. When I look at my forces, I don't care about distance. I only care about distance when I do a moment equation. I only care about distance when I calculate moment because moment is force times distance. So when I look at my free body diagram here and I'm summing up forces, I just care about the directions of the forces. So by convention, anything up is positive. So FA and FB are positive. The 800 is downward. Now, if this is a balance situation, then the sum of the forces, static equilibrium, says that it should be zero. So I know what FB is. That is 667 newtons. I know Wanda's weight is 800 newtons. So now I can go ahead and solve for FA. Move 800 to the other side, 800 newtons to the other side, minus 667. So the force in member A, or this FA force here, is equal to 800 minus 667. So about 133 newtons. Okay. So by Wanda standing off center and closer to the right-hand side, this here experiences more tension than the force at A. So when you have the students hold a meter stick and you put the weight closer to one person, that one person feels more weight. And so when they swap, this person gets to this side and they go, oh my gosh, it's much lighter over here. And this person that swaps over here says, oh my gosh, that's much heavier. And so you can actually feel the difference when it's off center. Okay. Showing that just because Wanda weighs 800 newtons and off center, the tension in A and the tension in B is not the same when you're off center. So it doesn't get split evenly like some students might expect. Okay. Now when it's in the center, it does. Okay. So let me go ahead and clear that out. And so we get to that question. Do you think cable at point A will experience the same force as the cable in point B? Some students will say yes. But when you do that meter stick activity where you hold that 5-pound weight or whatever you have, they can feel a difference when they swap places and they go, oh, it's not the same. And then mathematically, we can show that. Okay. So they went ahead and worked that out. So they took the moment about point A, the moment of resulting from Wanda's weight, and the moment resulting from the force of the cable at B. Okay. Now, we know that the sum of the moments has to be zero. So here we have that, again, equation 800 times 5 plus FB times 6. Okay. And so once you calculate that out, you get that and you can see the work here. Okay. So then we get to the conclusion and they have you hold this basketball straight out. Or the bowling ball, what's the moment generated on your shoulder? 15 pounds and then the length of your arm. Question 2, question 3. So the line of action of this force. So this one's kind of unique because what you'll do is you say, you know what? Here's the distance I'm given. I need a perpendicular force to that distance. Okay, so I need to figure out what this magnitude is here. Okay, so I have this 62 degrees here for this force here. So what I'm going to do is I'm essentially going to look at maybe making a triangle that looks like this. Right, here's my 90-degree angle. So if this is 90, what's this here? Well, 90 minus 62, right? So that'll be that angle there. And the x component of this force doesn't cause a moment about the shoulder. This component here does. So how do I get that component? Well, if I assume this is the y component, because I've got a coordinate system that's essentially rotated, right? Where this is x and this is y. So that's going to be equal to, um, actually, let's use this angle here, which will be 62 degrees. So opposite, so sine of 62 is equal to opposite, which is that y component, over hypotenuse, which is this 5.56 newtons. And so multiplying by 5.56 newtons on both sides, I end up with the y component. And that y component is what generates a moment about the shoulder here. So then you'll take moment is equal to whatever that calculates out to be, force times distance, which is 0.92 meters. Okay. There's a couple ways to solve it. I'm not sure how they solve this on the answer key, but this is one way to work that example out. Okay. So that's the activity 416 moments activity. If you have any questions, don't hesitate to reach out. And so I thank you for tuning in and following along. And I hope this was helpful. All right. Have a great day.